I'm Remzi, and I've been at Wisconsin for, so it is kind of long, it's 15 years almost now. So I'm getting to be an old guy, or am an old guy. And I'm going to talk about a little bit some things we've been thinking about very recently in this space between applications and storage. Once I heard Steve Kleiman say that it's amazing how we can spend so much time just studying the reading and writing of bytes. And what I'll hopefully show you today is that, amazingly, we still do some of these things wrong and in some ways in a fundamental way. So please feel free to interrupt me with questions, concerns, compliments, critiques, anything like that. So let me start by giving a little background. A classic trade-off that happens in systems, I think probably pretty broadly, as well as in storage systems, is what I'll call performance versus understandability. We often trade these things off. We make systems more complicated, harder to deal with, harder to program in order to make them higher performance. So instead of understandability, we might say we're trading off ease of programming or maybe ease of programming correctly. And let me give a few examples reaching outside of what I'm going to talk about today. Memory consistency models. How should we view a memory in a multiprocessor system when we have multiple CPUs and threads updating a shared memory? Of course, there's certain kinds of models people have, like a very simple model is sequential consistency. That's probably the easiest to understand, where you think about loads and stores interleaving on a shared memory. But weaker models exist. If you know about like x86, there's something called total store order, which basically means that code that looks like this, where if you look at it and you think about how it interleaves, you wouldn't think it's possible, but it is possible, and turns out, for both these registers to end up with a 0 in it at the end. And the reason for that, and I'm not going to get into the details of this, but it's actually not that complicated, but the reason is pretty simple. It's performance. And specifically, in this case, we want to be able to have a write buffer or a store buffer in each processor. So the move of 1 into X and the move of 1 into Y on CPUs 0 and 1, respectively, kind of sit there and are hidden from the global memory view. That makes the system run faster, but it makes it harder to program. But it's well defined. These are pretty well understood things, and people have studied memory consistency models, including some of my colleagues in computer architecture at Wisconsin, for many, many years. Distributed storage systems, all the rage these days, right? Your favorite NoSQL store, have the same kind of issue. They have a notion of strong consistency, where I should be able to read any writes that occur from other clients. But there are many weaker consistency models there as well. And there's actually a great tech report by Doug Terry. If you're interested in this space and you haven't read it, it's a great read. It compares all these things, or explains all these things using baseball as an analogy. So perhaps the only paper where somebody thinks that the way to explain CS ideas to technical CS people is through a sports analogy, because we're all sports stars. But actually, it's a great read, and you should read it, and it's a terrific paper. And again, the same kind of reason, the reason that these weaker models exist is the same reason that they did before, for performance and availability. In distributed storage systems, things fail. And when you have strong consistency, obviously, you lose performance and availability. What I am going to focus on today are not those two things, but something very simple and classic, local file systems. Local file systems often sit underneath all of those distributed storage systems, and so you could view them as a fundamental building block. And of course, those local file systems are also on your desktops, laptops, phones. They're everywhere. They're something we've studied for a long time. And what we're going to talk about today is file system crash consistency. And of course, you might be thinking, hey, we've studied this. We understand this completely. There's journaling. We built that years ago. Take the ideas of write-ahead logging from the database world, apply it to file systems. There's copy on write. Many file systems use that, which is actually very similar to database shadow paging that's been around for many, many years. Soft updates. There's some work we did on something called backpointer-based consistency a few years ago. Lots of different techniques focused on keeping a file system consistent after a crash. But, and this is where maybe the talk is going to hopefully get a little more interesting, is the focus is a lot of times just on file system metadata. It's as if the file system is saying to you, what I really care about is my own data. I don't really care that much about what you do with your data. That's, in fact, your business. And that seems a little bit funny. In the end, of course, what we care about when we build a file system is that we want people to use it and to use it correctly and use it with high performance to achieve what they want to achieve with it. It's just a tool. So we should think about applications too, and that's maybe one of my biggest points I'll be making throughout this talk today, that we need to push up a level and make sure we understand how applications are using storage in order to understand how to build the storage itself. So let me give an example, and then I'll get into an outline of the talk, and then we'll get into some more technical details. So let's say we want to do something simple. I'm going to describe an application update protocol. So let's say there's a file called /f on disk, and it has in it the string bar, okay? And let's say we want to update that. So in fact, we want to just update the 3 characters bar to foo, because that's what we do as computer scientists. So you can imagine years from now, people are going to ask, why is that their choices? But in any case, to do that, we just have a simple protocol. We're going to use a single system call, a p-write, a positioned write. So we write to /f at offset to the letters FOO. And we'd like it to, the file to end up like this, okay? Make sense? Simple. We have bar in there. We're going to overwrite bar with foo and end up with a foo. Now, the question you might have is, well, is this the way if this were like a database with this string were an entry in it, is this the way we'd like to do that? And the answer is, well, maybe not. We're kind of assuming that p-write is atomic, but p-write may not be atomic. In fact, let's assume it isn't. And let's assume, in fact, it's byte-wise atomic, but not more than that. And so if it's byte-wise atomic, in other words, any one character might make it to the drive, but if you write 3 characters, you're not guaranteed that all 3 will make it. You might end up with any kind of mix of letters like that. And if you don't like the byte-wise atomic, you can pretend these are blocks and the same exact issues arise. Okay? So we have to do a little bit more. And if you took a database course sometime in your life, you know the solution to most problems when you're having problems updating something is you use a log. That's what I remember hearing in database class. Maybe you heard something similar. Of course, I also heard don't use file systems. So let's forget that part of the advice. And just remember the logging part. And let's create a little protocol so we can actually update what's going on, update this file correctly. So we're going to create a log file. We're going to make a copy of the old data in the log. And then we're going to go ahead and modify the file. And then we're going to delete the log file. And we'll actually see this kind of protocol in some of the applications we look at a little bit today, later on. And if a crash occurs, of course, in this type of logging, we can just go back and say, oh, look, some bad thing happened, so let's go get the old data and restore the file to its previous consistent state. Okay? Make sense? Okay, so let's try again. Here's a protocol. We create a log file. We write to it. And in fact, we write the old data and what the first number is what position it was at, and then the second number is what size it is. But that doesn't really matter. We just write something about the old data there. Then we issue the p-write to the file itself. So here's the new data being written. And then we unlink the log file. We get rid of it. So then the question we have is, does this work? What do you think? Okay, so somebody says, hey, maybe Kurt says we should maybe do some f-syncing. That sounds reasonable. But actually the short answer is we don't know. And the reason we don't know is this actually works on some file systems. I'll talk about this in a lot more detail today. But if you run this on ext3 data journaling mode, and we'll talk more about these modes too, it turns out it works. So you could, in fact, be a developer. You could write this protocol. You could test it really carefully on a particular file system, like ext3 data journaling mode, which actually, if you don't know ext3 and its data journaling mode, what it's doing is it not only takes your metadata and puts in a log inside the file system before it goes ahead and updates it in place, but it also does that for user data. So it actually writes everything twice, so it can be slow, but it actually has these nice properties, like it ends up ordering all these writes and making sure that they are committed in a fairly nice way. Now, if you run the same exact protocol, this is what was being hinted at with this call for fsync, is it doesn't work on ext3 in a totally different mode, which is ordered journaling mode, which just is ext3 journaling metadata. And again, if you don't know all these modes, it's okay. We'll get into more details about that later. So the answer of whether this protocol works is it depends on which file system you're running on. And that's a little bit like the state of the art today is, well, if you know a lot about how these different file systems work, you can say. So if we wanted to make it work on ordered mode, we'll take Kurt's advice, throw some fsyncs in there. Sync the logs so that that first write is guaranteed to hit the disk before the second write is issued. So that sounds pretty good. Does this work? Well, it works on data journaling. It works on ordered mode journaling. But it actually doesn't work on a different mode of ext3 called write-back mode, because in that case, we don't even get the guarantee that something like the append to the log that occurs in the second step happens atomically. In fact, only a piece of it may be reflected. So to fix that, we add our own application level checksum to the second step. And well, does this all work? Well, actually, there's another step missing. It actually doesn't work on any of these file systems unless we add this step, which is we actually have to, in Linux, fsync the directory as well. Because if you don't fsync the directory, what happens is the data may be written to disk, and the inode may be written to disk, but the new log file that you created won't be reflected in any directory. So in essence, unless you force the directory, the dirty directory at that point to the disk as well, the protocol doesn't work. So what did I convince you of? Hopefully, this isn't as simple as it seems. And unfortunately, the state of the art is a bit crazy. It's a bit like you have to understand details of how file systems do all their internal machinery to know something like, hey, does my protocol work? And even if you're very knowledgeable, what you end up doing is you end up adding all of this boilerplate additional stuff around the simple work that you wanted to do was that p-write. And you have to add all this other stuff around it. And of course, that not only makes your life complicated and error-prone, but it also makes your system quite a bit slower. So that's the setup. Hopefully convince you there's something to talk about. So what we're going to do in this talk, we're going to do two things. I'm going to start by getting a little bit more into file systems and trying to understand what today's file systems actually provide in terms of what we'll call persistence properties. In other words, what types of guarantees can they make about the atomicity and ordering of system calls as they're executed upon the file system. So we'll study that and we'll build a tool to find some properties out. Then we'll take it up to applications and try to discover the kind of application protocols that we were just talking about and find out if they're vulnerable to crashes at various points in their sequence. So when we write a protocol, the question is that protocol correct? So we're going to build a tool to try to figure that out. So that's part one of the talk. And in part two, what we're going to do is we're going to, that's kind of a measurement part. In part two, what we're going to do is we're simply going to go a little bit beyond measurement and say, let's build something new. And what we're going to look at there are some new interfaces, some new systems we've been working on where we can get some mileage, build high performance protocols in the application level. And the key idea there is we're going to show that it's important to separate ordering from durability. That a lot of current systems actually conflate those two things. And by doing so, they make the systems a lot slower at the, but correct. And we're going to show that you can get correctness and performance by separating those two concerns. Okay, and then at the end, I'll conclude, and I'll also actually, just when you're going to get excited and think I'm done, I'm going to actually talk about just one more thing. You'll see what that is at that time. It's not an Apple product announcement, but so don't get too excited, but it's just something else we've been working on, and I'd be curious to share. I just kind of wanted to share with everybody. Okay, so any questions? I'd be happy to interrupt it during. I don't know what the format of the keynote is. If people have questions during, though, feel free to raise your hand or shout it out or run to the front, tackle me, whatever. So let's get into the talk a little bit. And I'm going to watch the time here, so you'll have to excuse me. They gave me a long slot, so you should, if it starts looking like I'm going to end early, I'll just talk more slowly, so you could sense that. No, I'll try to finish a little bit early, but who knows. So anyway, part one. Let's talk about measuring. And like I said, the first thing I'm going to talk about is file system persistence properties. So what are those? Persistence properties are pretty simple, which is basically given a file system and some operations, when a crash occurs, what kind of on-disk states are actually possible? And this is after, say, the file system runs recovery. And the assertion, what I've claimed already, and I'll claim it again here, is that the state of the art is different file systems simply have different properties, different persistence properties. And of course, that makes life difficult for anybody who wants to write an application because you're trying to write something that works however it's deployed. You don't know if somebody's running ButterFS or XFS or ext4 in some mode that you haven't tested on. So it makes life difficult, but that's just the reality, and we're going to show a little bit of that. And of course, it's hard to determine. If you look at modern file systems, there may be tens, hundreds of thousands of lines of code. And even if you ask the developers sometimes, and very seasoned people developing these complicated systems, sometimes it's hard for them to even say how their system exactly works under some particular scenarios. So clearly, anytime that's true, it means there's an opportunity for some clarity in all of our thinking, I believe. Okay, so when we're talking about these persistence properties, we're really going to talk about two different types of things. We're going to talk about atomicity properties. For example, when you do an operation, does it happen all at once or does it happen in pieces? For example, when you do a write, most file systems, if you write a sector, that'll occur atomically if you're running on a modern disk, because a sector write, the disk itself will make that atomic. If you write a block, some file systems make that atomic. If you write many, many blocks, virtually no file system makes that atomic. Other operations like rename, it turns out, very useful in a lot of update protocols to use rename. You write a new version of a file to some temporary file, and then you atomically rename it to the file that you were trying to update. That's a very common protocol. And that goes back to the FFS paper where they suggested that you should have an atomic rename. So we'll test that sort of thing, whether, say, rename is atomic under various file systems. So those are atomicity properties. The second type of property we're going to be interested in is our ordering properties. Turns out when you're thinking about crash recovery, you're often thinking about the ordering of how you update file system state. So if I do one write and then another write, sometimes sometimes I don't even know I'm doing this, but sometimes when I'm writing a protocol like that, you're assuming that one write will happen before the other. And that was what enables recovery. So we're going to test that sort of thing. If A happens before B in program order, like in a sequence of system calls, does it mean it's persisted by the file system in that order, or is the file system free to persist it in a different order? And of course, a lot of times file systems want to persist things in different orders than they're submitted for performance reasons, right? That thing we talked about the first slide, performance versus ease of understandability. Of course, it'd be much easier if everything just happened in order and synchronously. Okay, makes sense? Okay, so let me give an example. Here we have a couple of writes to file descriptor 1 and then to file descriptor 2, letters A, and B. And so when we're trying to figure out what could happen if we do the two writes in a row, what we kind of care about are the possible states that might occur after a crash. And here we'll see the state of byte 0, which might be A or B, or maybe something else, or in the state of byte 1, and then the size of the file, which is a piece of metadata that the file system is tracking. So we'll see a bunch of different states. Here's the initial state. The file has nothing in it and is size 0, let's say. File 1 and file 2 both have nothing in it and is size 0. This is a state that can occur if there's no atomicity in writing the data as well as updating its file size. So in this case, what happened, for example, what could have happened is the file system perhaps said, updated an inode to say, yeah, this file has 2 blocks, and maybe points to some blocks. But the data hasn't been reflected to disk yet, so the result is you get garbage in the file. That's a possible, and that shows a non-atomicity of data and file size, just an example. In this state, there's no write atomicity, so we tried to write AA to file 1 and BB to file 2, but we only got partial of each. So that means maybe the file system takes a big write and breaks it into smaller writes. And of course, again, this is at the byte level for simplicity. You can imagine this across blocks or sectors. Another possible state, depending on the file system again, is in program order, we issued write to file 1 before the write to file 2. But in this case, what we see is that file 2 was persisted, and then say the system crashed, and file 1 was never updated. Some file systems will allow this kind of reordering to occur, and some actually don't. And we can argue about whether that makes it easier to program or not, but that's just and it turns out to be a relevant property. And then this state 5 is the final state. So just an example of the type of post-crash states you can end up with, and then how you can reason about what that means in terms of atomicity of operations and ordering between operations. Yeah?
Remzi, why did you write AA, BB, not A, B, C, D to see if there's any crazy swapping of data? If for some reason the A's and the A's were swapped, you wouldn't notice because it's the same.
Yeah, that's a good question. Did everybody hear the question? The question is, in this kind of example, why did you write AA and BB instead of, say, A1, A2, and then B1, B2? So if we saw something weird happening, we would notice. I guess what I'm trying to illustrate here is behaviors that we believe are all correct by some implementation of a file system. And I think what you're hinting at is there's this even broader space of, well, people make mistakes in implementing those file systems, and they might do something crazy like swap bytes around. So we're not even going to look at that. We're going to assume that whatever people are building, they're kind of trying to build in the file system. And we're trying to just simply discover what guarantees you can have when you're using that file system in terms of atomicity and ordering. Good question. Other questions? Yeah? Great. Great. Okay, so question one was basically, when you measure something like this, are you measuring a property of the file system or of the file system and, say, the underlying storage, like the disks and so forth? And I'll show you how we do this, how we try to measure this in a second. And what we're really focused on is what is coming out of the file system, and then we can kind of model some sort of ideal storage. I think that point hints at something very interesting, which is as we switch from disks to other media, assumptions that you are making in these file systems, which is embedded deeply in the file system. Sometimes it's hard for even developers to know, like, for example, that where they're making assumptions about, say, a 512 byte write being atomic, suddenly might go away. You're running on an NVM that somebody probably in this room is developing that has maybe byte level atomicity. That's an interesting problem, and I think that's points to even kind of future directions to go. Now, your second question was, how do you even do this? Is this possible? Doesn't seem possible. And I guess if I said yes, it's impossible, then the talk would be over. So I'll go forward and assume something is possible. So what are we going to do? Well, we're going to build this tool. It's called BOB. We couldn't come up with a better name. It's called the block order breaker. And what it does is it tries to discover some of these properties of a file system. And it doesn't quite achieve it in a way that's wholly satisfactory, but we'll see what it does exactly in a second. What you do is you run some workloads. I'd like to say that this workload part is easy and generic, but really this is smart grad students sitting there crafting these workloads. So this is not automated except in the sense that grad students are automatons. So no offense to any grad students in the audience. They seem to be pretty smart though. So they figure all this stuff out. Then they run these workloads. Then we're going to trace the block I/O that comes out from underneath the file system. And we're going to track those. And then we're going to emulate a bunch of different crashes. So we're going to say, here's a sequence of updates to the disk. Let's generate many possible different disk images that could have resulted from a crash at some arbitrary points in that sequence. And then we're going to determine what happened. So we're not going to actually prove that the file system has a certain property, but we're going to show cases where that certain property does not hold. And that turns out to be, of course, much easier. It's like testing instead of proof of correctness. And so in the future, it might be interesting to say, well, how could you ever prove that a file system actually has a particular property? Yeah?
On this slide, in the last two,
Yeah.
you talked about crash as the intervening break in the states that produces the odd results.
Yeah.
Is there something less than a crash that can produce similar results?
Great. So the question is, I've talked about crashes as the thing that's causing these results or problems. Is there something less than a crash that could cause this sort of issue? That's a really interesting question. I haven't quite thought about that. Sorry? Oh, so like silent failure? Yeah, I guess the types of things we're looking at basically, obviously these systems, actually almost all of them work really great most of the time. And why is that? Because everything just works. All the data you write eventually gets to the disk. So anything that basically prevented everything from reaching the disk could lead to some problems that are similar to this. Now, what we're looking at is we have a sequence of updates, and we cut it at some point, and maybe we will reorder things too, and we'll say what happens if it happens to stop right here. But you could imagine if you somehow had a sequence of updates, and then you had a silent failure and missed an update, and then you continued. You could have similar problems. Now, that raises other issues, though, like how do you detect that even occurred so you know whether to fix it? Here, we're assuming you have a crash. You can actually run a recovery. And then still what happens? So it's kind of an easier case, I think, than what you're hinting at. OK, so just pictorially, so we make sense of it. We have a workload, we have a file system. We're going to trace at that level between the file system and whatever device is below it. That's a disk. And so let's say we see some writes, 1, 2, 3. We're going to track those. And then from those, again, we're going to construct all of these different file system images that could occur if a crash occurred while these writes are occurring. So we could get an image with just a single one of these writes. We could get pairs, 1, 2, 1, 3, 2, 3. Or we could, of course, get all 3 reflected to the drive. Okay, does that make sense? We're going to make all those file system images. And then on each, we're going to essentially run a file system recovery and determine, hey, what's on the disk? Yeah? Yeah, so in this simple case, and I'll talk about this more in a second, the question is, is there anything restricting you when you can do reordering and when you can't? There certainly is, and so coming out of a file system, as I'll talk about in a second, you see writes, for example, that change state, and then you'll see things that restrict whether, if you have a correctly behaving system, like the disk works, for example, you'll have operations like a cache flush, which will ensure ordering. Let's say you do write of one block, and then you do a cache flush, and then you do a second write. You'll assume that there should be an ordering, and we'll observe that. We'll obey that ordering. So we're not introducing orderings that shouldn't happen, but the orderings that we're playing around with are cases where somehow the file system thought it was okay to issue a bunch of writes to the drive and let the drive reorder them. So these are just legal states that can occur. Does that answer your question?
Yes.
Okay. So a little bit more detail, if we're doing these 2 writes, if we had a simple file system, you might see, let's say, a few block writes come out of it during those system calls. Like, for example, first writing the data, then the inode of the file, then the data of the next file, then the inode of the next file, but with no constraints. And in that case, if a file system just issued all of those writes, there's lots of different states we could end up with, choosing any of the 1 writes to complete, choosing any 2, choosing any 3, and then choosing all 4. But we might be constrained, too. So same workload. But let's say we had a soft updating file system. So soft updating file system might follow a rule that, for example, you never write an inode pointing to a file until the data block is already written out. So the file system might issue a block write and then say flush the disk cache, and then issue the inode write, and then issue the write to the next data block, and then another cache flush, and then another, let's say, write of the inode. And that constrains us, which is exactly the question that was being asked. So there's fewer states for us to generate in that case. So we're just totally obeying what the file system thinks it wants to allow in terms of ordering and seeing what the results are. Okay, just one more detail, and then I'll show a few results. So it turns out, for the sake of this study, the file system API is actually very broad, but we can just look at 3 groups of operations. We're going to look at file overwrites, file appends, and then we group essentially all directory operations, renames, creates, links, unlinks, all those things into, we'll just call those directory operations. And it turns out that's enough to see some of the differences across different file systems. And of course, we'll also vary some of the size of operations. So we'll do things like a single sector write, a single block write, or multiple block writes. And we're trying to see, again, whether the file system guarantees atomicity of these operations and whether it guarantees ordering of pairs of them. Okay. So here are the results. The results are actually blacked out right now, so you can't see them yet. But what we're going to vary along the x or horizontal direction are the different file systems and configurations we mounted them in. So you'll see ext2 and ext2 mounted synchronously on the left. ext3 in write back, ordered in data journaling mode. ext4 in write back, ordered, turning off node delayed allocation and data journaling mode. Btrfs in just one mode, and then xfs in a couple different modes. So those are different. Those are actually 5 different file systems in various configurations. And you're going to see what we test over here, what properties we're trying to show the file system does not hold, right? We can only show that it doesn't seem to hold this property. We're not showing that it holds it in its absence. For example, a single sector overwrite. When we do that, is that done atomically, or can we show cases where it's not? A single sector append to a file, a block overwrite, a block append, a bunch of things about whether certain operations are atomicity. And the last one being directory ops includes everything like renames, unlinks, because we found those behave similarly across file systems. On the bottom, we'll show the ordering behavior. And there you see pairs of operations. So when overwrite happens before any other operation, is that order preserved, or does the file system feel free to change that order? And so forth and so on, a bunch of different things like that. So let me show the results. An X in this table shows that that property is not held by that file system. So I'm going to walk through this a little bit. Let's look at ext2 first. It's kind of the most fun one to look at. ext2 on the left, as everybody knows, ext2 guarantees nothing. It's surprising it stores your data at all. In fact, it guarantees one thing, which is a single sector overwrite. It does align that with sectors of the disk. So if you're running on a disk, that will be done atomically. Everything else is not done atomically. No guarantee. You can see ext2 mounted synchronously, which is the right of those two columns, behaves a little differently. And particularly when you mount it synchronously, it does each operation one at a time. And therefore, ordering is preserved across all of those pairs of operations. Right? That's not surprising. If you force everything to disk and then you move on to the next thing and force that to disk, that's going to preserve ordering. Now, there's a big problem with that. It runs quite a bit more slowly. But it does make it easier to reason about what's going to hit the disk when. So that's ext2. Here's ext3. You can see a range of different behaviors from write back, which is kind of the least sensible ext3 mode, but a fast mode because it doesn't try to order data blocks with respect to their inodes and when they're written to disk. Ordered mode is a bit more sensible. And then data journaling mode, really we could only find one case, and it's not a surprising case, where it does not obey any of the atomicity or ordering properties we tested here. And that's a case where you're doing a very large multi-block write of a file. That's simply because if the write gets big enough, the journal and the file system in something like ext3 or 4 is of limited size, and it simply can't fit that whole update into the journal, so it breaks it into pieces and does it piecewise, which means any large write cannot be committed atomically. And that's, of course, true actually of all the file systems. So different modes of ext3 give you quite different properties. ext4 is similar, but also different in some ways. So they added some new features in ext4, like delayed allocation. That actually changed some properties of ordering. You can see some of the ordering properties are slightly different. And that actually in the field broke some applications, caused people to think about how to change ext4 to actually support old applications, which had inadvertently, or advertently, I guess, relied upon ext3 semantics. And then finally, you see Btrfs, different, but also similar, and XFS in two different modes. So without getting into that to too much more detail, what you can see from this are the persistence properties of these file systems vary widely. If you're trying to build an application, if you really want it to work and feel good that it works, you don't want to test it on one of these file systems or one of these modes of one of these file systems. You want to test it on all of them. So you have a very big challenge, which is not just coming up with a protocol that works in an abstract sense, but it has to work on a bunch of different implementations that are very complicated. And on top of that, we're not even telling you if those properties that we didn't see, we don't know if you can rely on those properties where there wasn't an X. We just, we kind of think that those probably are properties that hold, but we haven't proven that either. So it's kind of a problematic state of the art. So you can sometimes rely on the atomicity and ordering properties, but you're not exactly sure when. So this tool was just the first step towards trying to understand that, and I don't think we've really answered this question. We're just starting to think about it. Yeah? Great. So the question is, do you have to worry about the buffer cache when you do some workloads and you're trying to update stuff? Doesn't it just kind of get hidden up in the buffer cache? And then you don't see it at the block trace level, and therefore you can't explore it. So that kind of hints back to the how you craft these workloads question. And so we're pretty careful about creating workloads that we know are going to cause stuff to go to disk. There's been some other work, earlier work out of Stanford, Junfen Yang and Dawson Engler, for example. What they did a few years back is they essentially looked at what was in the cache and then tried to explore states automatically of what things could be written given a certain state of the cache. And they used some kind of neat model checking tools to do that. So you're right, you could kind of push this up a level, but then you kind of open up a very big state space, and it's very hard to search. So we kind of, the way we narrowed the state space is, again, by trying to be smart. We just kind of crafted the workloads. Good question. Other questions? OK. So that's the state of the art of file systems. It's when you say what guarantees are held, actually, I don't think anybody can really tell you for sure, because the code is very complicated. And even if you talk to the developers, I think they'll say what they are intending, but I don't know how strongly they can say that. But whether they know or not, the reality is file systems are different in the guarantees they provide. So what does that mean for applications? So let's study that a little bit. How am I doing on time? I'm doing okay. What we're going to talk about next are application crash vulnerabilities. The goals of this part of the talk is to understand what the application update protocols are. So what are the series of system calls invoked by an application in order to actually update the data that it's managing? So let's say you're building SQLite, like a database like that, and you want to see how it works. What's the protocol that it uses to update its database? Is it correct? So our goals are pretty simple. Figure out what the update protocols are, and then given the persistence properties that we just talked about of a particular file system, or maybe an abstract file system, determine whether the update protocol works. Is it correct or not? That's ultimately what a developer who's developing a file which you're going to, or a program that you trust your data with, SQLite, for example, stores probably tons of data that people rely on all the time. You want to make sure that it works so that if a crash does occur, something reasonable happens. So here's a protocol from Berkeley DB. What does it do? Creates a log, truncates it, then appends something to it, then writes to it. That's what a protocol looks like. This is just one of many protocols hidden inside of Berkeley DB. Is it correct? Does it make sense? Well, it's hard to know, right? It's hard to know looking at something like that. Is it correct or not? It turns out, in fact, this code is making some assumptions. It's assuming, for example, that the truncate is an atomic operation. It's possible in a file system that truncate would happen in phases. And if it did, this protocol wouldn't work. And actually, this protocol needs an fdata sync at the end, though I'm not going to show you exactly why. But it's hard to know these things when you look at just a sequence of system calls. So we decided we need another tool. This tool is called the Application Level Crash Explorer, ALICE, why not? And this is kind of similar but kind of different. We're going to run a workload, but we're going to obtain not a block level trace, because before we were looking at the file system and looking at a block level trace. Here we're going to look at an application level system call trace. And we're going to, of course, filter out some system calls, like things that aren't related to file I/O. And we're going to transform those into micro operations, these minimal atomic updates of file system state. And I'll show you what those are in a second. We're then going to apply some persistence models. Say we're going to assume that the file system has these atomicity and ordering guarantees. And then we're going to run for each workload or each application we're interested in, we're going to run a specific workload checker to say, hey, is the data stored like under SQLite or PostgreSQL? Is the data in there consistent, and is the data kind of what we expected it to be after we did all this stuff and essentially modeled, again, a crash? And we're trying to determine what happens after a crash. Okay, so let me talk about a few of those steps in slightly more detail. There's a large variety of system calls, even to write to a file to disk. There's write, pwrite, write v, pwrite v. There's mmapped writes. We transform all those things and other calls into just a small set of generic ops, like overwrite, append, truncate, link, whatever. And then we turn all of these into an even simpler set of micro operations. These are the bare minimum atomic things we'll assume we'll have as building blocks. And then the logical operations, which look like system calls, basically are built on top of those. So we have a writing of a block, the changing of a file size, the creation of a directory entry, and the deletion of one. So for example, if you're doing an append, you'd be writing a block or maybe a few blocks and also changing the file size. And whether or not those two things happen atomically, that's determined by which file system you're modeling. Okay? So it might be that the file system does atomic appends, and then you would get that. Or it might be that it does not, and then each of the operations could be split up, and then we'd explore all the states that result. Now, the persistence model is basically what we talked about already. It determines how a file system restricts the atomicity and ordering of operations. And what we're mostly going to focus on is a real minimal abstract file system, where we're basically looking at the weakest guarantees a file system could provide, like ext2, actually, in many ways. And we're looking to uncover application correctness issues, or what we call application crash vulnerabilities, that if you ran this application on some abstract file system that had very weak properties, it wouldn't work. But we can also model other file systems, and I'll talk about the results of looking at these application protocols on real file systems or real file system persistence models as well. And then here we're going to have another checker, and this part's a bit more complicated because after basically you're taking a workload update, an update protocol, let's say from some database or key value store, and then you're turning that into a bunch of these micro operations, and then you're saying, oh, what if we crashed here and we had this reordering or whatever? We're going to essentially then construct a file system image, run a workload checker on it, which is a very application-specific thing. It runs like the database recovery tool to try to fix up the database, and then we go in and see, oh, is the data that we expect it to be in there? And so those can be pretty complicated, and this checkers per application take a lot of time to build and are certainly hundreds of, maybe tens or hundreds of lines of code just to check, did this one thing behave in the way we thought it might. Okay, these are the applications we looked at. Key value stores like Berkeley DB, LevelDB, GDVM, LMDB. There's a lot of DBs out there, so we picked some of them. Relational databases, SQLite, PostgreSQL, HSQLDB, version control systems, Git, Mercurial. Distributed systems, we've taken some pieces of these distributed systems, like some bit of the protocol on the name node of HDFS to see how it does an update, and some bit of Zookeeper where it does some kind of update. And then we also looked at the VMware Player virtualization software. All of these use system calls to try to implement some kind of update protocol. So all of them, therefore, are candidates worthy of our study. And I think all of them are generally kind of used systems. So they're out there storing your data today, whether you know it or not. So what are the results that we get? I'm going to go through these pretty quickly. One thing we get out of this tool is these protocol diagrams. I'm not going to show many of these. In fact, I'm just going to show this one here. I think this comes out of Zookeeper. And you can see they all have this kind of similar flavor where they create a log and then do some stuff to it and then write to it. But what the tool is going to do is embellish the generic set of system calls with some of the requirements that are actually hidden in the protocol that we only learned by crashing at a bunch of different points and seeing what didn't work. So for example, in blue, I've marked down some places where there's actually a required ordering of operations that isn't obvious from the protocol, like that the first piece and the second piece have to happen before the protocol at the end says it's done doing a commit. The orange shows that the write has been embellished, this write to the log, that write has to be atomic. If it's not atomic, something bad happens. And I'm not going to say what that is. It could be like the database becomes corrupt or inaccessible, but something like that. And then green is, we're going to show, like what we're showing with green is that sometimes system calls are missing for correctness, or in other words, to be able to recover from a crash at a certain point and behave as expected, we needed an fdata sync that wasn't included in the protocol. So those are the types of things the tool produces from each protocol. Instead of just seeing a sequence of system calls, you get basically some, hey, this is what this protocol seems to be requiring. And of course, on given different file systems, like missing system calls could be a problem, of course. And atomicity may or may not exist depending on the file system, as well as the same thing for ordering. So where are the vulnerabilities? Well, here's the sum of the vulnerabilities we found for each of these applications. I've broken down the vulnerabilities into atomicity vulnerabilities of some kind, ordering vulnerabilities, or durability vulnerabilities. Durability ones are basically mostly things like you said that the transaction was durable, but it wasn't yet. Or, for example, you had something that was durable, and then much later you did something else, and that messed up, and that actually affected the durability of some very old transactions, which we found some cases of that as well. So you can see a few things. Across all the different applications we looked at and some of the different versions we looked at, we found potential vulnerabilities, places where there's assumptions about the atomicity of system calls or the ordering of them, and you could view those as those are bugs. That means that something bad could happen if you're running on the wrong file system. Now again, this was all done with an abstract, weak guaranteed file system, like a Linux ext2-like file system. The other thing you should notice from this is there's some applications that do better than others, certainly, like SQLite, Postgres actually were pretty good. We only found maybe one case in each, and I think even the Postgres case, I believe that one case was actually documented, like don't run it on a file system that does this thing. So obviously people, in fact, some of the developers, like we interacted a bunch with the SQLite developers, it was pretty clear that they had a very deep knowledge of all these problems. Doesn't mean that they implemented everything perfectly, but they were very attuned to understanding the semantics of all the different file systems that people run SQLite on, because they knew for SQLite to work that they had to understand those things. So kind of interesting. And of course, the ones that were probably the most flaunting of this kind of problem, or most kind of didn't care, were the code repositories. They're like, well, whatever. We just write some stuff out, and hopefully it'll get there. So your code is in. I don't know if that's good or bad, but it certainly seemed to be easy to find problems in that world. Okay, so some highlights of some other kind of things we noticed. In a few cases, we were surprised by people seemingly relying on atomicity across system calls, which basically no system guarantees. Some cases, there was this thing we called append atomicity was needed, where when you do an append, Sometimes you can get garbage in a file, depending on the file system, and a lot of systems broke terribly if there was garbage at, say, the end of their log. A few, I think 3 or 4 of the applications assumed small write atomicity, like a write of a 200 or 300 bytes, which you basically get on all modern file systems when they're running on a modern disk drive, which you might not get if you move to a different medium. This is kind of the earlier question. But that was kind of hidden in the code. And the tool would discover that sort of thing. And then people misuse fsync. But at the beginning of the talk, I talked about how people will do an fsync of data, but they'll forget to fsync the directory. That was pretty common, actually. And so some file systems, in turn, have started making that essentially kind of happen anyway, even if you don't issue the fsync on the directory. Now, what I didn't talk about, those are just problems. There are certainly consequences that come out of this that are bad, too. Data loss, silent corruption in some cases. Better cases, when things go badly, you get something like, I cannot open the database, and you have to do some extra work to get things up and running. So kind of a range of consequences come out of these vulnerabilities. Now, you might be asking, well, this is on this abstract file system that you found these vulnerabilities. What about, and there was about 70 across all the applications, how do they do on real file systems? And we can model that with the tool as well, because we have some sense of which persistence properties from the first part of the talk are actually delivered by the different file systems. And there are fewer vulnerabilities when you run on real file systems. So here's some different ext3 modes and ext4 and Btrfs. So instead of seeing 70 vulnerabilities across all those applications, you see maybe 10 or 20 or 30. So you can view the 70, that total number of vulnerabilities, is essentially the kind of the ceiling of what you might see on some perhaps abstract file system. And then the reality is that you would see a smaller number in deployment today because of just the nature of what each file system guarantees. And that means for some of the applications, they actually work perfectly fine on today's state-of-the-art file systems. Sometimes by design, sometimes who knows. OK, so this is ending the measure part of the talk. I just have a little bit. The second part, which is shorter, is about something we built. But what we found, basically correctness issues in all the applications we looked at, some more than others. And all types of issues were found with atomicity and ordering assumptions or durability assumptions, and that many of those vulnerabilities actually manifest on current file systems. And certainly, since they're potential vulnerabilities, some of them may manifest on future unknown file systems that we haven't built yet. It's really hard to know today when you build a protocol, does it work? Because nobody even tells you for a given file system that this is the model that we have, that this is the model we should expect from the file system. It's just kind of thrown together by a deep understanding of the file system, which is, personally, I think a ridiculous thing to require from an application developer, is a deep knowledge of how the file system is built. That doesn't seem right. And that's why people build in memory consistency world. That's why they build memory consistency models. They don't say, hey, just study how the caches work, right? If you just knew how the caches work, then you can write a concurrent program. That's not how to build a system that makes any sense. And so we're not doing a good job with that. OK, so part 2, this will go a little faster. A lot of our work does this kind of measure then build, and the measure part is always like bad news, right? So hopefully we'll end on some better news. We'll build something that works a little bit better, perhaps in the state of the art. One thing maybe I've convinced you of, maybe I haven't, is that ordering is a pretty common requirement in anywhere you're trying to build a crash recovery. You need ordering. You need to know this happens before that, so that when you recover, you can kind of piece some knowledge together. File systems do this internally, whether you're building journaling or some other technique. Applications do this using fsync. Within a file system, how that actually is achieved is, well, disks and other devices have caches, and writes are generally issued asynchronously for high performance. So that means the order that their writes are persisted does not match the order that they're issued in. So you use something like a cache flush command to ensure ordering. So if you want block write of A to happen before block write of B, you throw a flush in between there, and then you can guarantee that write of A happens before B, because A is persisted immediately. Similar to applications, as we saw, we'll use fsync pretty commonly to ensure ordering. So if you do a system call write of A, and you want it to happen before system call write of B, you put an fsync in between there, and again, you get the same guarantee. The problem is, in building this kind of system, is that we're conflating ordering and durability. Internally in the file system, we're forcing things to disk because we want those to go to disk first. And from an application perspective, we're using fsync to force things to disk, even because we want them to go to disk first. But what we don't really care if they go to disk right now. What we want them is to go to disk before something else. So we're mixing those two things up. And the cost, of course, is performance. Systems are slow. If you do a lot of fsyncs and build a correct protocol, for example, it's slow. It's wildly slow. So what we started looking at is something we call the optimistic file system. Its basic tenet is very simple. We try to separate ordering from durability. And what this is going to do internally is avoid cache flushing in the basic journaling protocol, and we'll talk about that in a little bit of detail, and then externally provide OSync, a different primitive to applications, to allow them to specify an ordering between writes, but not force anything to disk right away, which is amenable, therefore, to a high-performance implementation. We're going to see some benefits from that, in some cases much higher performance, and a reasonable consistency model, which is sometimes called prefix consistency, where when you crash, you don't maybe get the most up-to-date data, but you get an older, consistent version. So you always have something you can build back from when you recover. And it turns out that's useful in a lot of cases. Yeah?
Do you also have the ability to force durability?
Yeah, we do. Yeah. So if we say, if you really... Yes, that's right. And we can use all the old techniques that people at Michigan came up with. So that same issue exists, right? If you want to force things to disk, we have a way to do that. But there's many cases where you don't need to. Okay, so to understand a little bit how this OptiFS, optimistic file system works, we have to talk a little bit about how journaling works. So bear with me. Here's a simple example workload. We're just appending a block to an existing file, and we'd like that to happen atomically. So we'd like to update structures like a bitmap, which marks a new block allocated, and an inode, which points to the new block, and a data block, which contains the data of an append. We'd like all those to be updated atomically. And the journaling protocol is going to let us do that in more or less. So let's see how we're going to see how that works. Here we have memory at the top of the system. Memory is where updates are first reflected. They have to be reflected to the disk in a particular order for journaling to work. And the disk itself is divided into two pieces, a journal or log on the left, and then the file system proper where the data is going to end up eventually on the right. So in memory, we have the data block, we have the inode, and then we have the bitmap. And then we have these other little blocks that we're going to use, a transaction begin and transaction end. And this is ordered journaling in ext 3 or 4, which means we're not journaling the data. We're just journaling metadata and making sure that we get a consistent update of metadata. Okay, that's just how ordered journaling works. So the protocol goes like this. First, you write the data. Then you write the transaction begin block and the inode and the bitmap. That's the update, the metadata update. And then you wait for that to be done. And you'd actually issue one of those cache flushes. Then you do a commit. And the reason you don't issue that commit concurrently with the begin and the contents is if you issued them all, the disk might get clever, reorder those, write the begin and end, lose power, and then leave you with what looks like a consistent transaction, but the contents are garbage. So we order those. And then when all that data is committed, the metadata is committed to the journal, what we do is then we do a checkpoint. We actually write the inode and the bitmap out to their place in the file system. Make sense? That's kind of a typical journaling protocol. So if we think about the ordering required, it's the data before the begin and contents, before the end, and before the checkpoint. And if you're really paying attention, that's actually the real requirement is that the data and the transaction begin and contents are both issued before the transaction ended. Actually, there's no ordering between those two because the only thing that matters is that those two things are on the disk when the transaction commits. So that's the actual kind of graphical requirement. Make sense? I'll come back to something that looks like this, so it's worth making sense of it. Okay, so as we stated before, we're going to use cache flushes in this protocol in order to guarantee ordering. That's going to, a flush again ensures all dirty data in a disk cache is persisted before it indicates completion. So that means at this point we're going to do a flush, and at this point we're going to do a flush. So that's a lot of flushing for just a simple little update, and there's a big cost to it. It's really expensive to do this. So if you have Linux ext4, you can actually turn on and off cache flushing. In fact, people in the field, the performance was so bad. You can see the performance when you have cache flushing on under this varmail workload. Not a great workload, but it's a workload. You see the performance, if you turn off flushing, is pretty good. So in fact, people in the field started saying, yeah, let's turn off flushing. It's a great idea. It runs a lot faster. Most of the time, it's fine. And then the system crashes, and then maybe they're not as happy. But you can see what the cost of that is. When you're forcing ordering all the time, and you do it with these expensive cache flushes, performance is much worse, which is the left bar. So what we started thinking about is, can we get good performance but still reasonable consistency? The reason we're paying the penalty of those flushes is to guarantee ordering so we can recover and have consistency. Can we do something else? And that's what led us to think about optimistic crash consistency. Of course, most of the time the system doesn't crash, so that's kind of an obvious good thing. And what we're going to do is, in some cases, we're going to find that we could replace ordering with checksums. And I'll show you how we do that. It's an old idea. and we'll use it in a couple places. And then there's a couple other techniques that we use too to make this all kind of streamline and generally avoid cache flushes. We do assume a slightly different disk interface than is available today. I think it's actually a bit of a detail, but I'll tell you about that too. And then we have a new file system interface, which I already talked about, OSync, and then as Brian asked, desync if you really have to have durability. The goal of Octafs is to provide prefix consistency. Yeah.
Before you throw out flushing,
Yeah.
isn't it possible to think about it differently that you're always streaming, and flushing is just finding out that you streamed it?
Yeah, I totally agree. You could, and in fact, we've looked at that a little bit, and it kind of works almost as well. So basically, you let a bunch of things happen, and then periodically you issue a flush so that you just know that everything you've done beforehand is done. I think you can get pretty good performance with that. So this reflects a little bit more like our earlier thinking, and then we've been trying to do that because the reality is we're not going to get a new disk interface from the disk vendors anytime soon. It's a good point. So prefix consistency is what we're trying to achieve. Again, just to make it clear, what that is you do a write of, say, A, and you do a write of B, but you want A to happen before B, so you put an OSync between the two. And what we want to guarantee is that either nothing will be on the disk when this sequence is done, or A is when the sequence is done, or A and B, but never B without A. Okay, simple as that. Now you can use fsync and get kind of the same guarantees, but fsync forces A to the disk right away, and that's going to make things slow. Here we're not going to force anything to disk until much later. We're just going to make sure it happens in the right order or in the way that we can recover so that if the wrong order happens. So let's talk about how we did that. One of the basic ideas, and this is an idea we had a long time ago actually. In 2005 we were working on this paper called Iron File Systems. And the idea there was one of the students was working with us, Vijayan Prabhakaran, who for many years was at MSR actually and now is at Datrium. What he was kind of annoyed by how slow the journaling was. And what he realized is one of those pieces of, in fact, one of these pieces is that what we can do is in one of the places that in the transactional protocol, we have an ordering where we write this before that, we can actually use a checksum to replace that ordering. So in particular, we had that requirement that the transaction begin and its contents hit the disk before the transaction end or the commit block. What we can do instead is simply just have a checksum over the whole transaction. It's kind of a simple idea. Store the checksum in the journal itself, issue them all together, and then if you crash, basically as you're scanning through the log, you check, oh, does the checksum match the contents of the transaction? If it does, it means that all the writes hit the disk. If it doesn't, it means throw out that transaction. It didn't all commit, so you shouldn't try to recover from that partial transaction. So it's an old idea, like I said, from some years back, and actually this is, became part of ext4 and is ships part of ext4 today. What we did here is we extended that idea. We said we could do the same thing for data blocks. When you're appending a data block, you can actually also put a checksum of the data block in the log. And that way, when you just send everything to the disk, if you then crash, when you're recovering, you check, hey, the inode says it just had this new block allocated, and it points to that block. But now we have a checksum stored there, too, that tells us whether or not that data block is the one we thought it was. And if it's not, we're just going to discard that data. Now, that leaves us with one other problem, which is there's this other ordering dependency that once you do the transaction commit, you have to have the commit happen before the checkpoint. Now, the checkpointing happens much later in time. So there's a big time gap between those two things, which helps us. But we need to know that those transactions are complete in order to actually go ahead and do the checkpoint. So here we just assume we had a new disk interface, and that's not really realistic. We're just assuming the disk will tell us, yeah, all those things are done. You can now go on and issue the checkpoint. As Charlie was pointing out here, maybe we can approximate this with cache flushes maybe at a more periodic nature, and that's something we're actually looking into. But let's just assume we have this, and life is good. We're an academic, so we can make stuff up and say it's good, like most of this talk. So, okay, how does the protocol work here? Let's see how that works. Now we can issue all of these things at once. That's the data, the transaction begin and contents, and the commit block. We issue them all, but we have checksums so that if some of them don't reach the disk and we crash, we can tell. Simple. Then we get a notification from the disk. That's that asynchronous durability notification. It says, hey, that's all done. And then we can go ahead and issue the checkpoint. So we've turned that heavily ordered, complicated protocol into just, hey, issue a bunch of stuff. And then much later, you can do the checkpoint after you're told the first piece has committed. So that's what that looks like in terms of our graph. And we're replacing that ordering point with that asynchronous durability notification, not a flush. Even better, we can actually kind of pipeline this across multiple transactions. So you can journal the data. You can write the journal and issue the data of transaction 1, of transaction 2, of transaction 3. You can do all this work, and then later in the background, checkpoint them in order. And that allows you to really streamline performance. So I'm going to do a quick analysis, and then I'm going to wrap up. And that seems to be like I'm OK on time. We're just going to look at one. We looked at a whole bunch of workloads. And if you're interested, I could point you to a paper on this. The first part of the talk is not yet in a published paper. It's a very current work. But this part is published already. And what the workload we're here was we're just doing some SQLite table updates. And we're going to use OSync where it's appropriate. So instead of fsync, we're not going to force things to the drive. We're going to use OSync just to order things. And we're going to evaluate two things. Does OptiFS provide the kind of consistency we thought it does? And then how much does it improve performance? So how are we going to do that? Here we do simple analysis. On the right, we're going to show OptiFS. And on the left, in the middle, we're going to show two different systems, ext4 in what I'll call fast and risky mode, which is basically running ext4 but turning off cache flushes. And people were doing this, right? They just mount ext4. They're like using this whole journaling protocol, but they turn off cache flushes, so basically the protocol doesn't really work. But this is how they'd run it because it was really fast. But if you crashed, it might not be consistent, and therefore you'd have to run a full file system check to even repair it. And then all the semantics you were counting on are gone at that point. In the middle is slow and safe ext4, which is basically mounting it and doing all the cache flushing and that full protocol that we're talking about. So it's slow, but it's kind of correct. We're going to insert we have the sequence of writes that come out of this. We're going to insert 100 different crash points and then remount the file systems on those images and see what happened. And the first thing we're going to see is 73 out of those 100 experiments of crashing, the fast and risky ext4 gave you an inconsistent file system. So you're updating something, you crash. Because you're not forcing ordering using cache flushes, the bad thing happens. It's kind of an expected result. And it happens a lot of the time. You can see for both ext4 and OptiFS, that never happened. So that just means they're implemented correctly. They do not recover to an inconsistent file system, except unless there's a bug, right? But no bugs found in this test, or at least no bugs found at first, and then the typical graduate student iteration until that number is 0 is the way to look at that. How many times was the file system left in a consistent but pretty old state, like the state before you started doing the table updates? And you can see here the difference between OptiFS and ext4 and slow and safe mode is that OptiFS, more than any other file system, leaves you in the old state because it really runs far ahead. It kind of lets a bunch of stuff happen, but it doesn't commit everything all at once. And therefore, when you crash at a given point in time, you're more likely to go back to an old but consistent state. That's the trade-off we're making. And then you can see sometimes we left in the new consistent state. Last piece is performance. This is just the time per operation measurement. You can see the left and the right, fast ext4 and OptiFS are in the kind of 10s or 20s of milliseconds. I don't think there's anything too significant about the difference, even though OptiFS is a little faster. You can see the difference as compared to ext4. When you run ext4 in correct mode, it's 10 times slower under this workload. So 10 times slower and correct is what we were trying to get away from. So we were trying to get towards fast and consistent. And that's what OptiFS is. So in this case, 10 times faster and gives you prefix consistency, a different kind of consistency, but something you can work with and recover from as an application builder. Yeah? So the old one, basically, we're doing some, I don't remember the details of the workload, but basically it's, you do some updates to some SQL, some tables. And what old is basically saying is those updates didn't get through. So you just go back to the original, say, state of the file, of the tables. And then new means you got the updates went through. And there's some details to that, but that's basically what it means. Yeah?
So does OptiFS tell you that it's old versus new?
No, OptiFS never tells you that. And there's no, you're kind of stuck dealing with that. And this is an excellent point that Jeff is making. Basically, well, at some level, what is crash recovery? It's what can you deal with? In some cases, you could probably deal with the fact that the data is completely corrupt, too, if you have some other way of getting the data. We're assuming that's not true. What we're assuming here is that having an old version that's consistent is an easy way to build from. Sometimes you'd like to know that. Some applications, you absolutely don't want that. You want to know, hey, I committed this thing, and it's a bank transaction, and it's correct. This is not what this is for. But there's many cases, I think, where this works okay. But yeah, we don't have a way of particularly knowing that unless you keep some extra information in there yourself or something like that. Yeah, Brian and then Arez.
Well, it could be if that's what this is for, if you externalize much of screen.
Yeah, that's true. Yeah, no, I like the way you're thinking on that. That it basically depends what you're telling people about what you did, and we could have a much different. We could kind of change how we're doing that too to reflect kind of that line of thinking, and that works here too. Yeah, so it's perfectly complementary. Yeah, Arez?
So the one thing that kind of bothers me is that more often than not, you want about without the old state.
Yeah.
Means that, you literally have lost some data that
Yeah.
would have gone to
Yeah.
the database. That could be important data that
Sure.
appears in at least in exe or slow mode.
Sure.
That was there. Is there in Optimus kind of a initial trade-off you can make? Maybe you don't need 50.3 milliseconds. You can be a little slower, but you can bump, you can have more consistent new states.
So I'll take that as that's a good suggestion. I mean, we haven't thought about that explicitly. Like, could you have almost like a knob of freshness? We just say, this is what freshness occurs. You're saying, why not make that a knob? I think that's a great idea. We haven't looked into it. The other point to make before I get to Ashwin's question is, most of the time, you don't crash. So this is a very extreme case. We're finding in this whole update sequence, if we crash at all the points, what happens? But reality is, most of the time, you just run. So most of the time, you get the data you expect. In fact, it's in memory. So it's a little bit, to say we're mostly in the old state, I feel like, well, it's a little bit unfair to us because most of the time, you're not in this state where you crash. It's just when you crash, yeah, you go back in time a little further. Yeah. But good, I like that idea. I'll try to remember that. Yeah. Yeah.
You disable the asynchronous notifications and put the cache flush for that case because then you don't have to depend on it. Just the checksum, what kind of mode?
Yeah, so there was actually some students that did a project like that for a class project this past semester. What they were trying to do is get rid of this notion of having a different disk interface and basically in the background have a periodic flush that then we can transform into an asynchronous durability notification. Yes, everything you've written up till now is done. And in that case, we got something like 80 to 90% of the same performance here. And I don't think there's a fundamental reason that's any different, actually. So I think we actually can achieve pretty similar performance. Yeah, so I think that's kind of the answer there, is I think you can do pretty similarly. There are some other things I didn't talk about here. There are other cases and other workloads that cause more problems for OptFS. So this works very well if you're appending data. If you're overwriting data, we actually have to do more work to be able to recover reasonably. In that case, we actually journal the data too. In that case, we're slower. But I'm not showing that here because why would I show that? Yeah.
My other question is the exe4 fast is slower than OptFS because they have some hierarchical order? What's the...
Yeah, I don't think there's a fundamental reason. We've looked at that sequence. We stared hard at the kind of I/O trace coming out of that for a long time, and there were some cases where the OptFS IOs went out in a slightly different order, and therefore went faster. I mean, it does a nice job of kind of doing all the log writes first, and then doing all the checkpointing in the background. So you get just a slightly better. I don't think that number is significant, is what I'd say, but there are some niceties to the IO. Yeah.
It seems to me that some of the problems that you're addressing in this artifact are you can write into like a file system. For example, something like saying you've got a can't connect to awful, but
Yeah.
RFS,
Yeah.
Yeah.
That's a great question. The question, if you didn't hear it, was, hey, isn't journaling just broken kind of from a performance standpoint? Maybe the problems go away with copy on write file systems like ZFS or Btrfs. To some extent, that's true. Some of the properties of those file systems are very nice for performance. Where you get into trouble even with copy on write file systems, though, is what happens when somebody's calling something like fsync a lot. When they call fsync a lot, those file systems have this problem. They have to commit their new branch of the tree. So they're saying, well, how do you optimize that in ZFS? How do you make that fast? Well, it turns out then they use an intent log there to make certain operations like that go quickly. So a lot of those file systems end up using logging anyway. So you have the same exact question if you're calling fsync a lot. So maybe the answer for your question would be, if you have OSync, which is a different kind of guarantee, I think actually that would work very well inside of that type of file system, and I think it would do in similar ways. This type of workload runs very poorly on those file systems for the same reason it runs poorly on a journaling file system. It's just hard to commit things very frequently. And so I think the OSync would actually help in that case too, but we haven't shown that.
What about something like soft updating file systems, like
Yeah, soft updates, very interesting. I think kind of a conceptual file system and much different than all these. But the problem with soft updates is that you have so many more ordering points that you have to worry about. So because you're always forcing this out before that, before the other thing. So I think that actually has even more ordering concerns that you have to think about. And how OSync would work in that, I don't know. I think it'd be hard to figure that out. But interesting question. OK, so let me summarize this part of the talk and then wrap up. I'm doing OK. Optifast tries to separate durability from ordering, avoiding flushes internally, allowing applications to build with OSync. Can get performance and consistency, prefix consistency. Some of that prefix consistency idea is already in use elsewhere. There was a nice NSDI paper that used the same idea. And of course, in the future, we'd like to see where else this idea could be applied. Remember, I'm going to conclude. Now, it's just like, you're going to get excited. You think you're done, but I'm going to talk about just one more thing. So you'll have to indulge me. And again, nothing too exciting, just something we've been working on. So conclusion is, I think there was a surprising, at least for us, I mean, this is one thing. When you've been teaching something for 15 years, you're always surprised by things you haven't been teaching people, right? You're always saying, why have I not been telling people about this? It's because I didn't know about it. And the surprising thing for us here was how much lack of clarity there was around crash consistency. File system people know how to build file systems to deliver correct, consistent metadata, but it seemed like there had been less thought put into what the applications and their data, how we should care for them, and how you can program to them. So our first steps towards getting at this, we're building some tools. Those are not the be-all, end-all of tools, but just kind of hint at the problems. And then we looked at one file system where we kind of changed some of the guarantees to be more amenable to a high performance and crash consistent application protocol. But I think a lot more is needed. And hopefully I'll get somebody, maybe just one person, maybe nobody, maybe just myself, to think about what other tools we need to think about this problem, what other systems do we build to address some of those problems, and maybe some standards. Those other systems that I talked about at the beginning of the talk, memory consistency models, a rich and formal set of thought around it. Same thing with distributed storage systems, a lot of thought around eventual consistency, strong consistency. We should have the same kind of thinking and standardize some of that thinking so that when you build a file system, you can say, oh, that file system delivers this kind of consistency, and therefore you know how to build an application to it. We have to think about the impact of new devices. This is a question that Kurt was hinting at earlier, which was, hey, if you throw an SSD under here or an NVM, like Steve's building all his troublesome fast devices that don't have the same kind of atomicity guarantees, what happens? Does a file system work anymore? In fact, we posed that question to some file system developers, and they said, that's a really good question. It's hard to know. You have hundreds of thousands of lines of code. Maybe we should do like Steve says and throw out all those file systems. I don't like that, though. But I don't know. I'm just making up what you said. Steve hates file systems. So that's why he's sharing HotStorage. So you can, and I think the other last piece here is that you can't just study systems. You have to look above the level of, you always have to look at the level above, right, to know what is actually wanted, right? If you don't, then you're going to miss out on a lot of things. So we can't just study file system consistency and think about our own metadata. It's a little bit of a self-serving kind of thing. OK, so let me acknowledge and then the one more thing. This is work done by myself, led by myself and my wife. So I was Arpaci and she was Dusseau. I've told a number of you this story. So we hyphenated our names when we got married. But the real work was done by these grad students and a postdoc. There's some papers, including some that are in progress. If you're interested, I'd be happy to send you those things. And this is all supported through NSF and a data center research institute we call Wisdom. So feel free to visit the website. A lot of support from companies and NSF to make this all possible. So thanks to all of them. So the one more thing, if you'll indulge me, not too exciting, but something I've been thinking about for the last few years, which is I'm going to call the case for FOBs, which sounds like a vulgarity, but is not. A lot of people have been thinking in the educational space about MOOCs, massive online courses. What we've been thinking about are not the videos themselves, but where I started thinking about this is I thought about where did I learn in classes? And where I learned, frankly, was by reading books, in some cases really good books. So why are online classes free but books cost $100? Is a question we started to think about. So what we started to think about are that textbooks should frankly be free. There's no reason textbooks shouldn't be online. And there's a lot of reasons for that. Usually when you're writing a book, you're doing that because you want to share knowledge with other human beings. So the best way to do that is to make it available on a website. You make the material more easily found. Things like Google, for example, or Wikipedia can link to it. It's amazing. We've created, like, what is the web? Probably the biggest invention we'll see in our lifetime is the web, probably, maybe not. Maybe it's killer robots, I don't know. But maybe it's the web, which is this huge amount of information at your fingertips, except for textbooks, which are trapped, in the published form, hidden from you, a modulo Google book search. So amazingly, if you make them free and online, Google, all these tools that we built actually work. You can, if you want a printed copy, you can do it yourself these days. It's very easy. And frankly, nobody's making money off these books. Maybe the publishers a little bit. I've talked to a number of book authors, actually, and I say, hey, your book sells for $100. How much do they give you? One guy said they give me $1.25 every time they sell it for $100. Another guy said he gets $8. He felt pretty happy about that. Get $8 for every $100 book sale that's made. That's just insane. Why are we signing up for this? So anyway, we've been experimenting with this with a free operating systems book. We basically just have taught an OS course for many years. Now we just turn that into some kind of online book. And it turns out if you make it free, people start using it. So over 1 million chapter downloads over the past couple of years. And we're not even really done with the version 1.0, but people already start using it because Google will find it. You search for some topics, it'll point to the book. So just like anything that I talk about, it's an advertisement, but it's really a call for why are we writing books for publishers to make money? And if there are publishers in the room, my apologies. I don't mean to make you the target of anything, but I think if you're going to go to all this work to make your book, all this work into making a book, you should make it available as widely as possible. And you can still sell printed copies if you want to make a little bit of money, but you're never going to make that much money. My advisor was Dave Patterson, who's a very successful book author, and he used to tell me, you don't do it for the money. And if he doesn't do it for the money, it means, well, either means he's rich, which may be true, or it means you don't make that much money from it. So you're doing it for other reasons. You just want to create a book. So why would you want to trap it inside of the few printed copies that exist in the world, or Kindle copies, same difference, at $100 a pop? So anyway, that's something we've been working on, and that's the end of my talk. So thank you. Hey, so some questions? Yeah, Kurt, go ahead.
So first of all, there's a bidding war going on right now on a contract out on you between book publishers and
File system developers.
Amazon. So just so you know.
Sounds good.
So a few comments. Something minor. Earlier, that big slide with the X's on it.
Yeah.
I think if you change the X's to check marks,
yeah.
so kind of invert that, I think it would be more, a little easier for people to comprehend.
Okay.
Secondly, so invert it, in other
Yep,
words.
I got it.
Secondly, I think you misspoke a couple of times when you said...
Just a couple of times.
Yeah. You also on your slides, you were inconsistent about...
And out of order, too.
where you said that the notification, the checksums obviate the need for... one point you said obviate the need for ordering, and another point you said it obviates the need for flushing. So which is it? I assume it's obviating the need for flushing, but not for ordering, right?
No, so I did mean both those things. Now, it may not be, for what it's worth. So what I'm talking about in that case is there was an ordering implied in the original journaling protocol, A before B, let's say.
Yeah.
Transaction begin and contents before transaction commit. So there's an ordering in that original protocol.
Okay. So
that ordering is implemented by a flush. So write the first things, then flush, then write the second things.
Okay.
So essentially, when we added that simple checksum, which is again kind of an old idea, we're getting rid of both of those things.
Okay.
So I do talk about those interchangeably, but it's like one is the logical thing and one is the implementation of that thing.
So you might explicitly say it obviates the need for both.
Yeah, that makes sense.
And lastly, and this is where I'm going to beat you up a bit.
I thought we got through that part already.
You invited us to do that.
Okay, yes.
So since you're in academia, it's wonderful. Actually, it's really good work, and it's very relevant work, and valuable. But I think one thing that you may be leading people to believe, although probably nobody in this room, is that if you do, if you do the things in OFS, you'll basically make applications completely reliable and
Well, I don't know
mission
about
critical
that.
and so on.
Yeah.
And I think as some of us asked earlier,
Yeah.
the reason why a lot of databases go to a lot of trouble and in fact don't use file systems in many cases, it's not just about performance, but it's because it's not, you're kind of assuming that
Yep.
the file system is the center of the universe.
Yep.
And of course, database people think that database is
Yep.
the center of the universe,
Yep.
and they're right. And the reason is because you have to be
Yep.
concerned about not just bugs in file systems or
Yep. Yep.
properties of file
Yep.
systems,
Yep.
but their data corruption can come from things like garbled writes,
Sure.
misdirected writes,
Yep.
lost writes,
Yep.
which, as you said, is very
Yep.
hard to detect, right?
Yep. Yep.
And so, the need for a very robust crash recovery
Yep.
mechanism
Yep.
is going to be there no matter what, even if you do all the things that you suggest.
I totally agree.
And that's because it's hardware failures,
Yep, yep.
cosmic rays,
Yep.
et cetera.
And I think that's, those are concerns that are very valid. There's actually some excellent work at HP that I found out about recently. I actually gave a similar talk. Actually, Charlie invited me to give that talk, so thanks for doing that. And I was exposed to some work which actually addressed that exact question. Hey, when we're running these commercial databases, which are built, like you said, by these genius database guys, because you're a database guy. and people have looked at these problems for a long time, right? So you run Oracle or whatever. I don't know what databases they're running. Commercial is what they told me.
Yeah.
And what they did was they said, let's watch the stream of writes that go out over a SCSI bus, and then let's do kind of similar techniques, actually. So we had concurrently kind of come across this same problem. They approached it at a different level, and they looked at commercial systems. And they said they still have yet to find a system that works under all cases. And so I think the problem isn't so much a lack of awareness in either camp. And I would totally agree with your assessment in some ways, like these open source file systems and storage systems built on top of them aren't as far along as the database crowd, but even the database crowd, even really advanced developers, make mistakes. Like the people who built LevelDB are some of the most, seasoned programmers inside Google who built much of the infrastructure that the world runs on, but they would make mistakes. Like, they assumed that these two writes would go out in order, and on ext4, which they were running, it always did. So I think you're right in the sense that people have been thinking about this, and there's a lot of machinery out there to deal with a whole broader range of problems. Even in that world, people, I think, run into issues. And so I think we need to think about it a little bit more carefully and provide even more tooling so that people can test lots of things and see where their assumptions they're making are kind of broken. But I think I largely agree with your point.
So I'm a computer architect by training, used to be anyway. And
hi, Steve.
So it sounds, to extend the analogy between this and consistency models, you just gave us a new consistency model with a new set of arcane, difficult to understand kind of instructions that I have to learn to apply in the correct way.
Yes.
And the way that we deal with this in architecture is that you have pthreads, and inside pthreads mutex lock, there is like the 5 lines of magical assembly that does the right thing on whatever architecture you're running on. So and not just you, but all of these system call interfaces that we use to do this ordering stuff, it's basically asking the developers to program in assembly using these very low-level primitives.
Yep.
So it seems like maybe the right answer is to think about a higher level interface that we should be providing to the application so that they can, say things more
No, and this
clearly.
actually goes straight back to the database expertise, actually, because eventually what you realize, and I kind of agree with this, is, well, of course we should just have transactions, and that's the kind of unified programming model for concurrent, persistent updates. And if you just implement transactions correctly, everyone can build on top of that, and that gives it's actually even better, a higher level primitive than lock, unlock. It's here's all the stuff I want it to happen. So I think that's true, and I think it's hard to argue that that's anything but a good primitive, something higher level like that. So in the worst case, let's say, or in the best case, let's say everybody does program that way, then we still have this question of, are we building those transactional systems correctly? And the type of things that we're thinking about, are for that level of people, not the people, the kind of average programmer. At the next level, there's this other kind of reality, which is despite all the effort of the database people, somehow people just like using file systems. And so whether or not that's good or bad, people just, it's really easy. You open a file, you write some stuff to it, you throw some fsyncs in there, and you ship the code. So whether or not it's good that people program in assembly, as you called it, it seems to be a reality. So maybe we're also dealing with that reality. But I'm all for higher level programming abstractions and then trying to make sure that those are correct. Great point.
So I'm totally not going to be able to form this well, but I'm going to try.
Okay.
So, because there's, and this comes primarily from my experience thinking about teaching introductory programming.
Yeah.
And one of the things that new programmers do really quickly is that they start down the path of premature optimization.
Yeah.
And I wonder if we haven't just sort of done that by fiat in file systems.
Mm-hmm.
So how often do we actually need?
Yeah.
I don't. Partly it's because I don't do anything useful now that I'm in administration, but I probably never need a high-performant file system on my desk.
Yep.
And so, is there any reason to think about going in this direction? And maybe this is a longer conversation over beers tonight, but do you have any thoughts about that?
No, that's a great question. That's exactly what I've been thinking about that quite a bit. So it's great that you hit on that after just a few moments of thought. It took me many months to get there, so one day I'll catch up to you. That's why you're the dean. So in any case, look, where does all this really stem from? Our deep-seated fear of bad performance starts and ends with the disk, right? That world is changing. So you could view this, thanks to things like Steve is doing and other people are doing in this room, as an opportunity to say, why don't we not obsess so much about every last ounce out of the device, because the devices are getting pretty darn amazing. And let's think about starting with correctness as a basis. And so I think and this kind of gets a little bit back to Steve's comment about programming models. Can't we start with kind of like simple, correct programming models? And then only in those cases where people are absolutely convinced that there's a performance problem.
So add performance to correctness rather than the other way around.
Yeah, exactly. So I think that's a pretty rich direction to explore. And I think I think it's a good time because of the change that's going on technologically. Why do we have 100,000 lines of code? It's to manage the fact that the disk is so slow and we want to do all this stuff fast. And so, maybe it's a good time to come out from under that and rethink it. And I know some people are already doing that. So, yeah, that's a nice point. Yeah.
One last question, my standard question.
Okay.
You took tracing, can I have them?
Sure. Yeah, no problem. We're happy to share anything. Everything we do is open, so we're happy to share any piece, any tool, any file system, anything else. All right. Oh, looks like one last question.
One more.
Okay.
I'm actually going to disagree with Steve and say I really like that table that you had with all the various consistency, what gets broken. I was curious whether you'd shown that table to the developers of the various file systems and asked them, fill that table out for me.
Oh, right.
And see what they would come up with.
Yep. We haven't done it as a quiz. I think it was Kurt that didn't like the table. So you just wanted to invert it. The reason I didn't invert it, by the way, is because we felt like we only showed that the properties that were broken. So I didn't want to show that even though I like to talk about it like the other properties exist. We have talked with the developers. The Linux developers in general, file system developers, are great to interact with. I mean, what's nice about that world is you send them questions and they reply, often at length, and the better and more detailed your question, we found, the longer and more detailed the reply. So it's kind of an amazing crowd, and I've always been really impressed with how interactive they are. Sometimes we would ask them a very detailed question about some of these results, and it was clear that it wasn't obvious to them what the answers were. And I don't want to name anybody in particular, but there's a few file systems, and you'd ask, hey, what if this happened? Do you know what you're actually guaranteeing? And they would say, I think. And we're like, well, here's a sequence where this bad thing happens. And they're like, oh, yeah, I could see why that happens. So I think it is somewhat challenging to fill out those tables and just by knowing. And sometimes there are surprises in there. So we need better ways to think about that. And if not, it's just going to be guesswork. Oh, well, thanks. Oh, yeah. No, thanks very much. Yeah, that's a great idea. I love that's a great idea. Make it a quiz. Yeah.
You've got these, the OSync and the durability sync that
Yeah.
it's going to require the rewrite of different applications in order to use these different operations.
That's correct.
Have you investigated maybe predicting what the developer meant when they give in fsync?
Yeah, no, that's a great question. That's funny. We actually were just talking about that because we built this tool that finds these vulnerabilities in crash recovery. So recently, one of the students was actually thinking the same thing, of taking one of the Alice tool, it was called, and saying, hey, can we automatically replace some of these fsyncs that are in here with osyncs and then test, does the recovery still kind of work? So we started to look into that, but I don't have a great answer. But I think it's a nice idea and maybe has some promise.
All right, thanks.
All right, thank you.